Hi guys, I wanted to give you a quick introduction to what nuclear magnetic resonance spectroscopy is all about. It is probably the most powerful tool that we have in gaining insight into structural information about the organic compounds we synthesize in the lab. NMR involves an interaction between electromagnetic radiation, radio waves, and the nucleus of an atom. We will focus on carbon and proton NMR, and what we learned is the connectivity or the framework or the general structure of the compound. So protons and neutrons in the nucleus behave as if they're spinning. If there's an odd number of protons or an odd number of neutrons, then we end up having a net nuclear spin. And those are nuclei we can see easily in NMR. For example, proton, carbon-13, nitrogen-15, fluorine-19, and phosphorus-31. The spinning charge in the nucleus creates a magnetic moment, and this magnetic moment creates a magnetic field. So this magnetic moment exists perpendicular to the axis of nuclear spin. If we look at the normally disordered magnetic moments of atoms, and we take and expose them to an external magnetic field, which we'll call B0, their magnetic moments will align with the field, either with or against the field. A beta spin state is one that is aligned but is opposing. So it is the one that is aligned against, and that's much higher in energy. An alpha spin state is aligned with the magnetic field, and it is a lower energy spin state. When an atom with an alpha spin, that's the lower energy, is exposed to radio waves with just the right energy, the photon is absorbed and the spin flips to the beta state. The stronger the magnetic field, the greater the energy gap. So the more energy that it takes to flip. Up till now, we've been talking about the nucleus, the protons, and the neutrons. This magnetic field also affects the electrons. It causes the electrons to circulate, inducing an opposing magnetic field, or diamagnetism. The nuclei that experience less magnetic field are said to be shielded, requiring less energy to flip the spin. So they are shielded by electrons that are right around the nucleus. Nuclei that are surrounded by less electron density are said to be deshielded, so they're more exposed to the magnetic field, requiring more energy to flip it. The amount of radio wave energy that is necessary for that flip from alpha to beta depends on the electronic environment of the atom. It depends on the position of the electrons around that nucleus. When an alpha spin is flipped to a beta spin, energy is absorbed, and the atoms are said to be in resonance. This is not the same term resonance that we talk about when we're pushing electrons and creating stable conjugate bases. It's the same term, but a completely different concept. And the amount of energy required for each proton to spin flip tells us about its electronic environment. It tells us about where the electrons are around that nucleus, and ultimately then it tells us about the structure of the compound. So nuclear magnetic resonance requires a strong magnetic field, and it requires radio wave energy. The NMR that's in the organic lab is a 60 megahertz instrument, and the NMR that's in the research lab is a 300 megahertz instrument. Instruments go up to 900 megahertz, even 1,000 megahertz. And so those are used to look at structures of, say, proteins and antibodies. And so the stronger the magnetic field means that there's a higher energy gap. And so it takes more energy to flip from the alpha spin state to the beta spin state. You get more information, more detailed, you get more resolution, higher signals, better separation. It's just a much better signal. But for the purposes of an undergraduate lab, the 60 megahertz instrument is just fine. So in order to prepare your sample, we talked a little bit about this in the other video. We need to take our samples and prepare them neat in a liquid solution, which is a deuterated solvent, and then be placed in a small NMR tube. The sample has to then be placed into the instrument, and it's put into a magnetic field, and the tube is spun at a high rate to make the sample homogeneous and to alleviate any kind of variations in the tube, imperfections in the tube. So deuterated solvents have to be used. The purpose of the deuterium on the solvent is so that we do not get any signal from the solvent. Remember, we're looking at protons. We're looking at where protons are, what carbons they're on, how they're connected. So if our solvent, which remember, we put just a couple drops or a couple crystals of our sample So, and then we filled it with the solvent. So if we had a solvent that had hydrogens on it, it would completely blow out our signal. And so we're going to use deuterated solvents in all cases for proton NMR. And this is a schematic of an NMR instrument. This does, if you remember, look similar to the 300 megahertz one that we have for research. So when we're looking at an NMR spectra for evaluation and interpretation, there's 4 primary things that we're going to look at. So using the spectrum below, I will explain all 4 briefly. The first is the number of signals. You can see below we have 3 different types of protons in our molecule with the 3 different peaks. The second is the location. So one is near 1, one is in between 2 and 3, and one is near 7. That tells us about the protons. The third is the intensity or the area under the peak. And so we can see that there's a different number of hydrogens responsible for each of those peaks depending on the area under the curve. And the final is the signal shape. The signal near 1 has a 3-peak signal, and the signal in between 2 and 3 has a 4-peak signal. And so that also tells us much about the way the molecule is put together and the framework of this molecule. There will be a separate video about each of these 4 topics, and you can delve in deeper in all cases. Good luck!